right, so in this question, we are given three statements that talk about the behavior of two sequences, so a sub n and b sub n. And we're just trying to see which one of these statements are true. And so the first statement says that if a sub n and b sub n are both convergent sequences, then a sub n plus b sub n is also a convergent sequence. So this is true. And you can usually test these kind of statements with a pretty simple sequence example actually. And for the first question, it's gonna hold if you use any two convergent sequences. So I'll use a simple example. So a simple convergent sequence would be, we could say that a sub n would be 1 over n. And so with this one, the first term, so a sub 1 would just be 1, and then a sub 2 would be 1/2, and then 1/3, and then 1/4, and then so on and so forth. And you'll see that these fractions, they just get smaller and smaller. And so when you have 1 over infinity, that just becomes 0. And so this first sequence is going to converge to 0. And then we could do the same thing. This question isn't saying that the sequences have to be different from each other. So we could also say that b sub n is also 1 over n. And then this is also going to converge to 0 as n gets bigger. And so when you add these two together, you end up with another convergent sequence where you just have 0 plus 0 equals 0. Where, yeah, a sub n plus b sub n equals 0 plus 0, which equals 0. And so, yeah, so the first statement is going to be true. And then the second statement says that if a sub n and b sub n are both divergent sequences, then a sub n plus b sub n is also a divergent sequence. So this is only sometimes true. It's not always true. And so for the sake of this question, I'm going to say that it's false. And similar to the first statement, you can come up with two sequences to prove this. Or what you can actually do is you can either do that, or you can think up of a sequence that consists of two terms, where together they convert and kind of work backwards, if that makes sense. So I'll show you both situations. So we could say that we have a sequence. We can just say, I don't know, c of n is equal to n minus n. So what you'll see is c of n is n minus n. So on its own, by itself, this is going to converge to 0. It's always going to be 0 because n minus n is going to be 0 no matter what n is. And then you can split this into two sequences and say that a sub n equals n and b sub n equals negative n. When these are separated, you have two separate sequences that diverge, where a sub n diverges to positive infinity and b sub n diverges to negative infinity. So they both diverge, they're just going in opposite directions. But then when you squish them together and sum them together, they cancel out and they end up converging to 0. And so that would be a case where where you could have two divergent sequences that converge when you add them together. Because usually, generally speaking, with divergent sequences, you can add something to it that makes it a convergent sequence. And so, yeah, that's why 2 is only sometimes true. But for the sake of this question, it's going to be false. And then for the third statement, if a sub n is a convergent sequence and b sub n is a divergent sequence, then a sub n plus b sub n is also a divergent sequence. This is going to be true because there isn't ever a situation where you can add a convergent sequence to a divergent sequence to make it convergent. Basically, the divergence of a sequence is going to always overpower a convergent sequence, if that makes sense. You'd have to, if you want to make it convergent, you'd have to cancel it out with the right divergent sequence, like with the example I gave for the second statement. And you can try it too, where I'll even show you. I'll use two simple examples where you have a sub n equals 1 over n and b sub n equals n. When you add these together, since b sub n diverges, since b sub n is just going to keep getting bigger and bigger, while a sub n just gets closer to 0. And so you end up with a situation where it's like this goes to 0, and then this goes to 0, and this goes to infinity, so you just end up with 0 plus infinity equals infinity. And you can kind of see in this situation that there isn't really any sort of sequence that converges that you can use to cancel out the b sub n. And so as a result, yeah, so 3 is also true. And so for this question, the true statements would be 1 and 3, so the answer is going to be A. All right, so in this question, we're dealing with another set of statements, but this time the statements have to deal with a series rather than a set of sequences. And just looking at these statements, I have a feeling that it's going to deal heavily with the divergence test. And I know this because, well, I mean, the word divergent is in all three of the statements, and there's a limit as n approaches infinity in all of these statements. And so for this question, it's really just seeing how well you understand the rules of the divergence test. And so to start, I'll write down what that is. And so the conditions for the thing with the divergence test to start is I'd say out of all of the tests that you can run on a series, the divergence test is probably the most rudimentary one. And so, yeah, so basically what you do is you just take the limits of the series as n approaches infinity. So I'll use a sub n in this case since all of the statements deal with that. And if that limit is not equal to 0, then the divergence test says that the series will diverge. And so when we look at the first statement and the third statement, you'll see that the limit does not equal 0 in both of them. And so the statements 1 and 3 are both true. So I'll check those off. And the reason why, with the first statement, we know that the divergence test says that if the limit of the series as n approaches infinity does not equal 0, then it diverges. That doesn't equal 0 part, that includes the infinity or does not exist case. So in this case, dne does not equal 0, so it would diverge. And then in the third case, the limit is equal to 1/2, and 1/2 is not equal to 0, so these statements would be true because both of the series are divergent in those cases. And the thing is, the reason why the divergence test works in that sense, to test for divergence, is because when the limit is not equal to 0, in these series, you'll see that there's a sigma here and a sigma here, so that's a summation. And so basically it's just the terms are adding up together. And when the limit is not equal to 0, these terms are going, I guess, just further and further into some monstrosity, I guess. And so that's why series diverge when with the divergence test when the limit is not equal to 0. The problem statement, the problematic statement for this question is going to be 2. 2 is only the second statement. So 2 is only sometimes true. But for the sake of this question, I'm going to say that it's false, because it's not always true. It's only sometimes true. And the reason why is because this I'd say the second statement is kind of a bait statement, actually, because it's going under the assumption that only the divergence test was used on it. But the thing with the divergence test is, since it's the most rudimentary one, and kind of, I guess you could say, the most straightforward test, the problem is it's also not very powerful because the divergence test can only test for divergence. It can't test for convergence. So on the off chance, let's say that the limit of a sub n as n approaches infinity is equal to 0, that does not automatically mean that the series converges. When the limit is equal to 0, the divergence test is going to be inconclusive. And from there, you'd have to move on to a more powerful test. And so in this case, I'll use an example of that. And so since the divergence test can only test for divergence, there are cases where the limit of the series is equal to 0 and it still diverges. So for example, like you could use the, I guess I'll use a simple one. So let's say that a sub n was equal to 1 over n, like this, where n starts at 1 and it goes to infinity. So if you run the divergence test on this series, it's a simple series, you're going to find that it equals, that the limit equals 0, but it still diverges. And so as a result, this is a case where the series diverges, but the limit wasn't equal to 0. And so as a result, the answer to this question is going to be E, because only the first statement and the third statement are always true, where the second statement is only sometimes true. Yeah. All right. The sequence a sub n is defined by the recurrence relation, where a sub 1 is equal to 1, and a sub n plus 1 is equal to a sub n squared minus 1. What is a sub 5? So this question is just asking, basically just asking how do sequences work, pretty much. And so for this question, I'm going to set up a table to find this, because this question can be solved just by plugging in numbers and going up to a sub 5. Because in this case, n is just whatever like this number or this number is going to be. And so let's say, so it's asking us to go up to a sub 5. So I'm going to write a sub 1, a sub 2, a sub 3, a sub 4, and a sub 5, like this. And it's asking us what a sub 5 is going to be equal to in relation to this recurrence relation, where a sub n plus 1 is equal to a sub n squared minus 1. And in this case, a sub 1 is going to be equal to 1, because it's given to us here. And to find the next terms, we just plug in the previous term because it's n plus 1. So if n is equal to 1, then n plus 1 is going to be equal to 2. So when n equals 1, then n plus 1 is going to be equal to 2. So then a sub n plus 1 is going to be equal to a sub 2. So from there, and then here it says a sub n, and we know that n is 1, so we can just plug in 1 here, and you'll find that it's 1 squared minus 1, and that equals 0. And so now we have a sub 2. And then we can do the same thing and move on to a sub 3. And since the previous term was equal to 0, we'd put 0 here instead. And you'd have 0 squared minus 1, and that equals negative 1. And then for a sub 4, the previous term was negative 1, so you'd have negative 1 squared minus 1. And that also equals 0, because negative 1 squared is positive 1, 1 minus 1 is 0. And so then, this time now we're going to plug in 0 into here, and we'd have 0 squared minus 1, and that equals negative 1. And so now we have a sub 5, and a sub 5 is going to be equal to negative 1. So the answer to this question is going to be C. Alright, so we're dealing with this series of negative 1 to the k times the arctangent of k over k factorial. And it's asking us what the behavior of this series is going to be. And so you can see right away that this is going to be an alternating series because of this negative 1 to the k term here. And so with each k term, it's going to flip between positive and negative. And so that's going to give us a few additional conditions that we have to look out for. The thing with alternating series is finding convergence or divergence for them. Generally speaking, is you'd use other tests to get to a conclusion, but there's just a couple other things that you have to look out for. So I'll write those things down when it comes to an alternating series. So the first thing you have to look for is I'm gonna say that this series is gonna be, wait, that's a very ugly sigma. Give me a second. I'm gonna say that this series is equal to a sub k. Just so when I do refer to this series, I'm just gonna write a sub k instead of this entire thing. And so in this case, we know that if the absolute value of a sub k, or the series a sub k, if that converges, if this converges, then the original series without the absolute value, that is another ugly sigma. So the original a sub k, that's also going to converge absolutely, like this. And so, yeah, because with the alternating series test, it's not just divergence and convergence. You have absolute convergence and you also have conditional convergence. And so there are 3 possible things that you have to look out for instead of the usual 2. And then I guess you could also say the inconclusive case, but yeah. And so in this case, this is the criteria for an absolute convergence of this series. And then let's say that the absolute value of a sub k, let's say that diverges. then that leads us to a couple of other things. And so the thing we'd also have to check is to see if the limit of that series as it approaches infinity, if that equals 0, and we know that the series is decreasing, then that leads us to conditional convergence. And then otherwise, then it diverges. No, otherwise, no, let me right here. The original series, so without the absolute value, would converge conditionally. Otherwise, the original series of a sub k is going to diverge. And so those are the conditions that we have to look out for with those are the additional conditions that we're going to have to look out for with an alternating series. From here, we can start to try using other things to get to a conclusion. And you also notice that in the answer choices, it never mentions the alternating series. And that's because to get to a conclusion, you're going to end up using a different test to get there. It's just that the alternating series portion here adds additional conditions like conditional convergence, absolute convergence, yada, yada, yada. So for this one, for this series, I see a factorial here. And so that's kind of making me want to lean towards something related to the ratio test. If you do the divergence test on this, you're going to find that it's inconclusive because the limit of this series is equal to 0. And then for the integral test, as powerful as it is, there are conditions that you have to look for beforehand to do an integral test. And also try integrating that. That's not going to be fun. So the integral test, I wouldn't really do it here either. And so that leaves us with the ratio test. And the ratio test says that we have to take the limit within an absolute value. So the limit of as k approaches infinity, absolute value of a sub k plus 1 over a sub k. And if this limit is less than 0, then the series will converge. And if it is greater than 0, then it's going to diverge. And if it's equal to 0, then it's going to be inconclusive. And so now I'm going to set up our terms. So we know that a sub k is equal to this series. So that would mean that a sub k plus 1 is going to be equal to -1 to the k plus 1 power times the tangent inverse of k plus 1 over k plus 1 factorial. And so now that we have all of our terms, now we can set up our limits. So we'd end up with a limit as k approaches infinity of and then also I'm gonna get rid of the alternating portion of these series or these terms because we're dealing with an absolute value. So that's gonna eliminate negatives. And so we can simplify this down already and say that we have the tangent inverse of k plus 1 over k plus 1 factorial divided by the tangent inverse of k over k factorial. And so from here we can take our limit and we can simplify things a little bit. And so there is a way we can get rid of these factorials. And so, let me use a simple example. So let's say we know that 3 factorial, that's equal to 3 times 2 times 1, which equals 6. And so you'll know that with whatever number it is, with a factorial, you just multiply it with the next number down until you reach 1. And so if we were to use a variable, let's say we had n. So n factorial, that would be equal to n times n minus 1 times n minus 2. And you'd keep going down all the way until n is 1. So until you reach 1. And that's what n factorial is equal to. And so you can use that to get rid of the factorials here of k plus 1 and k factorial. Since we know that n factorial is equal to this thing over here, we can say that here, or actually let me also rewrite this limit to show you what I mean, why we're going to cancel things out. Since we're dividing two fractions here, this limit can be rewritten as the absolute value of tangent inverse of k plus 1 over k plus 1 factorial times k factorial over the tangent inverse of k. And so now we can start canceling things out here, since this is in the numerator now and this is still in the denominator. And so we can say that we're dealing with a case of k factorial over k plus 1 factorial. And then this would be equal, going back to this thing I mentioned over here, this would be equal to k times k minus 1 times k minus 2 all the way to 1. And this would be equal to k plus 1 times k, because it's just 1 minus 1, times k minus 1 times k minus 2 all the way to 1. And what you'll notice here is that even though this is a k plus 1 and this is just a k, since these both just go reduce down to 1 eventually, we can cancel out all of these terms over here. And so this, and all that's left is this k plus 1 term. So this fraction just simplifies down to 1 over k plus 1. And so our final limit that we end up with a limit here that says that the limit as k approaches infinity of the tangent inverse of k plus 1 over k plus 1 times the tangent inverse of k. And from here, now we can finally take the limit. And recall that when you're dealing with a tangent inverse term, the limit the tangent inverse of infinity, that's going to be equal to pi over 2. And then the tangent inverse of negative infinity is going to be equal to negative pi over 2. And the reason for that is if you were to graph this, if you don't remember why, when you graph the tangent inverse of something, you end up with a graph that looks something like this, where you have a bottom term line here and a top line here, where the graph is going to bottom out at negative pi over 2, and it's going to top out at pi over 2. And so since we're going towards the positive infinity direction, this line is going to get closer and closer to pi over 2. And so that's why the limit of, that's why the tangent inverse of infinity is equal to pi over 2. And so this limit just becomes the limit as k approaches infinity of pi over 2 over infinity times pi over 2. And then these cancel, and so you end up with 1 over infinity. And now we just have a bottom heavy fraction, and so we know that this limit is going to be equal to 0. And 0 is less than 1. And so as a result, this is going to, since we use the ratio test to get here, we know that this converges. This converges by ratio test. And then also, going back to the fact that we're dealing with an alternating series here, the fact that we got here, the fact that we found that the absolute value of this series converges through the ratio test, this leads us to the original series will converge absolutely. And so this series is absolutely convergent, but since we got here using the ratio test, that's why it's going to be D, because it says that it's absolutely convergent by the ratio test, not conditionally convergent, because the absolute value version of this series did not diverge. We ended up with this scenario. And so this is the most straightforward case of an alternating series, which is nice. So yeah, so the answer to this question is going to be D. What are the values of P that will make the following series converge? So we have a series here of just ln of n to the p power over n, starting from n equals 1. And we're trying to figure out, the thing is, since we have a variable here, this p, the behavior of the series is going to change depending on what p is. So from here, it's just a matter of figuring out a kind of test to use to get to a conclusion where we can isolate the problem down to where the only thing that we'd have to change to make this thing converge would be p. I think for this one, I'm leaning towards using an integral test. And the reason why is because, well, there's a couple things you have to look for when considering an integral test. Is you have to make sure that the series is continuous, and you have to make sure that it's non-increasing. And the reason I'm saying non-increasing is because there's a difference between non-increasing and decreasing. Non-increasing includes the case where you could have like two terms that are equal to each other while it still continues to go down. whereas decreasing, every term has to be strictly less than the previous one. Um, and so that's why I'm using non-increasing instead of decreasing. And you can use an integral test on a non-increasing series. Um, and so um, and then the last thing you have to make sure is to make sure that the series is always positive. And so and positive within the interval that we're looking at. So the interval that we're looking at here is from the interval that we're looking at is from 1 to infinity. And so from this interval, if you were to graph this series, or no, you'd have, well, no, there's a p here, so you wouldn't really be able to graph it. But depending on what you set p to, it's going to be um, it's going to be positive within this interval. And so I'm going to use, so yeah, so then I'm going to, and another reason that I'm leaning towards using an integral test for this is since we've met all the conditions, so continuous, non-increasing, and positive. Also, ln of n, no, ln of n over n, that's a pretty easy integral to do. It's just you can solve it by just using a u substitution. So I'll set up the integral. Now the problem is, since we are going to use an integral test for this, we're also going to have to adjust the lower boundary as well. Usually, generally speaking, you could just say that the lower boundary is going to be equal to whatever n is equal to here, and then the upper boundary is just infinity. But you'll find that if you use 1, you're going to get an undefined answer no matter what p is. And so so instead of using 1, I'm going to use 2, and it'll make sense once we fully evaluate this integral. So the integral that we're going to come up with is going to be from 2 to infinity. And the reason you can do this is because since we're going to infinity, the difference between 1 and 2 is so minuscule in the grand scheme of things that it makes an insignificant difference. And so that's why I set it to 2 instead of 1. And so then the integral is going to end up looking like the natural log of n to the p power over n integrated with respect to n. And so since we're integrating with respect to n, we can treat p as a constant. And so the first thing I'm going to do is I'm going to set up our substitution. So you'd say that u is equal to ln of n, and du is going to be equal to 1 over n dn. And so as a result, dn is going to end up being equal to n du. So now that we have our substitution, we can also adjust the boundaries since we're integrating with respect to u. So the new integral, this is going to be equal to the natural log of 2 and infinity. And so we end up integrating u to the p power over times n over n du. And then these two n's are going to cancel, and so our new integral just ends up being this integral, so u to the p du, and then that just equals u to the p plus 1 over p plus 1. And we can do that because we're integrating with respect to u, so p is just a constant. And then we'd evaluate that from the boundaries of ln of 2 and infinity. And so when we plug things in, we're going to end up with an integral, or no, we're going to end up with the limit as, I'll just use b, as b approaches infinity of what is it, of b to the b to the p plus 1 of like this. Or no, you know what, no, I'll just keep it in terms of u, just to not make things too complicated. So you end up with as u approaches infinity of u to the p plus 1 over p plus 1. Depending on what p is, this can either go to infinity or this can go to 0. And the thing is, we want this, and then also we're going to subtract this. We also have to add a subtraction here of ln of 2 to the p plus 1 over p plus 1. So I'm going to focus just on this limit for now. We'll worry about this term later. But the thing is, we want this integral to converge. And so from here, this is the part where I was talking about, where all we have to do is just figure out a number for p where it'll converge. And so as you know, so this limit, depending on what p is, it can either go to infinity or it can go to 0. And the way it works is if p plus 1, if p plus 1 ends up being positive, then it's going to end up going to infinity, because this u term is going to end up staying in the numerator, so this fraction is going to get bigger and bigger. And so what we want is a p-value that sets it so that p plus 1 ends up being negative. And so for that, you could just say that we can just set p plus 1 equal to 0, and we'll find that p would be equal to -1. And we want and actually, let me rewrite this again. We'd want it to be, we'd want to set up an inequality. We'd want to say that p plus 1 has to be less than 0 because we want a negative number. And so in that case, we'd end up with p is less than -1. And what this does for us is if p is less than -1, this will allow this u term, this will make this limit go to 0. Because let's say, since we want p to be less than -1, let's just use like -2, for example. So if we have the limit as u approaches infinity of u to the -2 plus 1, so that equals -1, over -1, this limit would be equal to 1 over -1 times u. And then this limit is going to go to 0 instead of infinity, which is what we want. Because if it went to infinity, then that would mean that the integral diverges, which would mean that the series diverges. And so we'd want p to be less than -1 in order for this integral to to converge. And then also you can see here, the reason why I used 2 instead of 1 is because if we used 1, we'd end up with ln of 1, which is equal to 0, and the problem is then you'd end up with a situation where this integral would diverge no matter what p is equal to, because if you kept p positive, like I mentioned earlier, then this limit over here would go to infinity, and then this would be defined, but we have an infinity here, so it would end up being undefined or diverging because of this infinity. This infinity would overpower this. Now, if we set p equal to a negative number, then this limit would converge to 0, but then this would become undefined. So if we use our -1 term here, we'd end up with ln of 1 to the -1 over -1, and that's equal to 0 to the -1st power, which is undefined because this would be equal to 1 over 0, and you can't divide by 0. And so that's why I used 2 instead of 1 for this original integral. And so yeah, so now we know that this series is going to converge when p is less than -1. Not less than or equal to, it has to be strictly less than because we want a negative number. And so yeah, so the answer to this question is going to be B. All right, find the sum of this series. So 1 over k plus 2 times k plus 3. So this is actually it's probably pretty more simple than it looks. This is actually going to be a telescoping series, and you can find this. The way to do that would be you can actually do a partial fraction decomposition on this term here, and when you do that and you split this up, you'll find that it's going to take the form of a telescoping series. So I'll do that. So to set up the partial fraction decomposition, you'd say that you could say that a over k plus 2 plus b over k plus 3 is equal to this series. So just 1 over k plus 2 and k plus 3. And the cool thing is, yeah, since it's also, I feel like that's what this question wants us to do, because the k plus 2 and k plus 3 term are already factored out nicely for us. And also the decomposition is pretty simple. It is just as simple as just having an a and a b term here, because there's no exponents or repeating terms or any of that other stuff. So we have the form of the decomposition. So now we just have to find what a and b is. And finding that is also pretty simple. We can just multiply each term by k plus 2 times k plus 3. And so when you do that, you end up with a times k plus 3 plus b times k plus 2 is going to be equal to 1, because this is going to cancel itself out. And then, yeah. And then to find a and b, we can just set k equal to -3 and -2 to cancel things out one at a time. So I'll start with -3. So when we say that k is equal to -3, then this will cancel out the a term, and we'd end up with 0 plus -1 times b. So just -b, which equals 1, and then we'd find that b is going to be equal to -1. And so that's one term out of the way, and then we can do the same thing to find a, except we'd set k equal to -2 instead, and that'll cancel out the b term. And so when you do that, you end up with a just equals a plus 0 equals 1, so a equals 1. And so we have the decomposition now, and now you can probably see how this takes the form of a telescoping series, because our split up term, this is going to become 1 over k plus 2 minus 1 over k plus 3. And since we know that this takes the form of a telescoping series, we can apply tests related to the telescoping series to find the sum of this series. And so what you'll notice is you'll see that we have a k plus 2 and a k plus 3 term here. And so I'm gonna show like the first few terms of k to show you how things are gonna cancel out over time. So when k is equal to 1, I'll start with 1 here. So when k equals 1, we end up with 1 over 3 minus 1 over 4 in parentheses. And so that's for when k is equal to 1. When k is equal to 2, we're going to add another term here and say that it's 1/4 minus 1/5. And then we're going to add another term for when k is equal to 3. And you'll say that you'll find that 1/5, you'll end up with 1/5 over 1/6. And what you'll notice here is that this 1/4 is going to cancel out with this 1/4. So these can cancel. And then this 1/5 is going to cancel out with this 1/5. So these are also going to cancel. And we can keep going. And you're going to find that all of these intermediate terms are going to cancel each other out, no matter how far you go out. So we could go like all the way out here and just say that, and we can just say that, I don't know, 1 over k plus 2 minus 1 over k plus 3. It's gonna and this k plus 2 term is going to cancel out with the k plus 2. Or wait, no. Let me actually. I can show this in a better way. This is gonna keep going. We can end up saying that you'd end up with a term like 1 over. We could say that 1 over k plus 1 over k plus, or no, I'll say plus 1 here, and then plus 2. And then this is supposed to be a minus, my bad. Plus 1 over k plus 2 minus 1 over k plus 3. And you're going to see that with no matter what k is, these two terms are all the first term of the latest pass is going to cancel out with the last term from the previous pass every single time until you decide to stop. And so all of these intermediate terms are going to cancel with each other except for the very first term and the very last term, because this 1/3, since it's the very first term of the series, it's not going to get canceled out with anything. And then the very last term from our latest pass of whatever this is, then this 1 over k plus 3 term is only going to get canceled out if we add another term here on top. But if we stop here, then you just end up with everything cancels out, and you can just end up with this sum would be equal to like 1, or no, you could find a limit saying that we can say that 1/3 minus 1 over k plus 3. And we can find the sum of this series by taking this limit as k approaches infinity. And when you do that, you're going to end up with 1/3 minus 1 over infinity. And since this is 1 over infinity, that's bottom heavy, which would mean that this is going to just go to 0. So this would just be equal to 1/3 minus 0, which just equals 1/3. And so 1/3 would be the sum of this entire telescoping series. And so as a result, the answer to this question should be A. Alright, so we have another set of statements that we have to work with relating to the series A sub n for this question. But this question is, there's a couple other conditions that we have to look for that are very important. And so you'll see here is that it says that we have 3 statements that are given about a series A sub n with all A sub n is greater than or equal to 0. This A sub n is greater than or equal to 0 thing, that is very important. Because this is going to change a lot about the validity of these statements below. because the fact that it says that all of a sub n is greater than or equal to 0, that eliminates the possibility of a sub n being an alternating series. Because if a sub n could have been an alternating series, then the validity of these statements would be a little more complicated. And so the fact that we don't have to worry about alternating series makes our life a little bit easier in this case. So I'm going to start with the first statement that says that if a sub n is divergent, then a sub n to the n power is also divergent. So that is not true, or at least not always true. And the reason why is I'll show you an example. Usually for questions like this, I like to look at what the statement says and then come up with an example that matches that statement that disproves that. So in this case, we have a series to the n power and then just a series without a exponent. And so you could try to come up with a series that goes to the n power that you can find the convergence of using the root test. So I'll use a simple example here and say that first I'll say, oh no, I'll start with the first statement that says that a sub n is divergent. So you can use a simple term here saying that a sub n a sub n equals a sub n is going to be equal to just 1/2. So this is a case of a series that diverges, and you can find the divergence of it just by applying the divergence test to it. If you take the limit of it, it's just going to go to 1/2, which isn't equal to 0, because it's always going to be 1/2. And it diverges because it's a summation, so it's just going to be 1/2 added to itself over and over again, and it's just going to go to infinity. And so that's why this diverges. The difference, though, is the moment you make this go to the nth power, you're going to find that it actually converges. So instead of a sub n, let's say now we have a sub n to the nth power, and that would be equal to 1/2 to the nth power. Now that it's going to the nth power, now this is actually going to converge. And the reason why is you can prove this by either using the root test or by looking at the geometric series test. And the reason why is because in this case, if you look, since this is a geometric series, you're going to find that the r value is 1/2, because this 1/2 is that's r. And a geometric series test says that if the absolute value of r is less than 1, then the series converges. Otherwise, it diverges. And in this case, the r value is 1/2, so it converges. And then you can also look at this by using the root test. If you take the limit as n approaches infinity of the nth root of the series, so 1/2 to the nth power, this is going to be equal to 1/2. And the root test says that if the limit is less than 1, then it converges. If it's greater than 1, then it diverges. And if it's equal to 1, then it's inconclusive. So it has the same rules as the ratio test, but with a different limit that was used. But the limit goes to 1/2, which is less than 1. So with the geometric series test, we've proved that it converges, and with the root test, we've also proved that it converges. And so this is a case that just disproves the statement where you set the series to the nth power and it ends up converging. And so yeah, so the first statement isn't true. Now the second and third statements, they're basically just saying the same thing, just they're basically just saying the same thing, and they're actually both going to be true. And the reason why is because we know that the original series a sub n is convergent. And so since we're dealing with a convergent series, that means that the series is going to converge to some number. It's not going to turn into some infinite monstrosity. And so when you're working, so if you have multiple different series that converge, since they all converge, even if you put them together and things like that, it's still going to converge. Because, for example, like let's say you had a sub n and b sub n, and they both converge. So these both converge. If you add them together, it's just a convergent series plus another convergent series, and so it's still going to converge. And then that's one of the fundamental properties of a series that converges. And similarly, that also holds for if you multiply two convergent series together. So like let's say a sub n converged to 2 and b sub n converged to 3. If you add them together, then you get 5. 2 plus 3 equals 5. And then if you multiply them together, you get 2 times 3 equals 6. And they both converge. And so that also that proves the third statement. And then the second statement is just it's saying the same thing, but you're just multiplying more series together, I guess. And so as a result, yeah. It would change if if it was a divergent series. Like if you had two divergent series, then it would be a little different. But since we're dealing with convergent series, they behave nicely. So you can add them together, multiply them together, and it'll still converge. And so yeah, so the answer to this question should be D. All right, find the sum of the series 2/3 to the m power. So right off the bat, we're looking at a geometric series here, and also it's asking us to find the sum of the series. So if we can also assume that the series it does converge. And I know that we're dealing with a geometric series here because this series is it takes the form of like a r to the whatever m power, and where r would be equal to 2/3. And I know that this is a geometric series because with a geometric series, like when you graph them, like they always converge to something if it's a convergent series. So like it would go, if it was like a positive, it could be like this, and it converges to something, or you could have like a geometric series that looks like this that also converges to something like that. And so anyway, we know that r is equal to 2/3, and the geometric series test says that if the absolute value of r is less than 1, then the series will converge. And in this case, it's 2/3, so it does converge. And to find the sum of a geometric series, that would be equal to a over 1 minus r, where r is this value, so 2/3, and a is whatever the first term of the series is. And so in this case, we're starting at m equals 4, and so to find the first term, we'd plug in 4, since that's the first value we're starting with. So a would be equal to 2/3 to the 4th power, which would be equal to 2 to the 4th power over 3 to the 4th power, which just equals 16 over 81. And so now we have a and r, and so we can find what the sum is. And so the sum of this series would be equal to 2/3 over, no, not 2/3. 16 over 81 over 1 minus 2/3. And then this can be further reduced to 16 over 81 divided by 1/3, which would be equal to 16 over 81 times 3 over 1, which just equals 48 over 81. And then this can further be reduced. If you divide both terms by 3, this can be reduced down to 16 over 27. And so now we have the sum here. This is going to be the sum of this geometric series. So the answer to this question would be B. All right, what is the smallest number of terms of the convergent series over here that must be summed to be sure that the partial sum is within 10 to the negative 3 of the true sum? So we have a alternating series here, and we're dealing with a partial sum like the question says. And since we're dealing with an alternating series here, this is definitely something related to the alternating series estimation theorem. And what that states is that the partial sum, so let's see, the partial sum of s minus s sub n is going to be equal to the next term from the latest series. So that would be like if this series is called a sub n, then a sub n plus 1, and it would have to be in this case, and it's going to be it says that the next term is going to be within whatever given term, or like within what margin of error we want. And so in this case, the margin of error that we want would be 10 to the negative 3. So this would mean that the next term would have to be less than 10 to the negative 3 of the true sum. And the reason it's less than and not less than or equal to is because it's saying within. And so it's safe to assume that they're talking about it being like, because if it was less than or equal to, they would have specified that. And so as a result, it would just be less than. And so from here, all we'd have to do is come up with a term for a sub n plus 1, and then solve for n, and it'll get us close to, and it'll get us to our answer of how many terms of the series we would have to sum up to get a partial sum that's within this value. So the first thing I'm going to do is find what a sub n plus 1 is. And since we know that a sub n is equal to this series, a sub n plus 1 would be equal to 1 over n plus 1 cubed. And so then we can put this into our inequality. And I'm going to rewrite this 10 to the negative 3 as 1 over 10 cubed. And then 10 cubed, that's 1,000. So our final inequality is going to look like this, where we have that 1 over n plus 1 cubed is less than 1 over 1,000. And then from here we can solve for n to solve our inequality. So when you do that, you end up with 1,000 is going to be less than n plus 1 cubed. And then we can find the cube root of 1,000, which would give us 10. So that would say that to get rid of this cube here, so we'd end up with 10 is less than n plus 1. And then we can move this one to the other side, and we end up with a final inequality that says that 9 is less than n, or n would have to be greater than 9. So what this inequality tells us is that we need to have n has to be greater than 9 in order to have a partial sum that's within 10 to the negative 3 of the true sum. And since it's greater than and not greater than or equal to, we'd have to go 1 up. And so that would mean that we would need 10 terms instead of 9. So 9 plus 1 equals 10. So we would need a total of 10 terms that would need to be summed to satisfy this condition. And so as a result, the answer to this question is going to be D. Okay, so now we have another question dealing with a series and trying a series and seeing what the behavior of that series is. And so for this kind of series, you can also see it in the answers, but you can usually, for a series like this, you can come to some sort of a conclusion by using a sort of comparison test. Doing it with a direct comparison might be a little finicky, so so definitely going towards a limit comparison test would be better here. Not to mention all of the answers have a something related to the limit comparison test. Another thing also, I'm already gonna get rid of E because you can do a divergence test on this, and you're gonna get 0. And when you get 0, when you take the limit of the series for the divergence test and get 0, that means that's inconclusive. So the divergence test isn't going to tell us anything for this series. And so from here, yeah, the next thing we'd have to do is do some sort of comparison test. And with a direct comparison test, part of the reason why it's kind of hard, there's not really that many situations where you can really use it and get a conclusive answer, is because you have to worry about whether your comparison series is greater than or less than your original series. Whereas with the limit comparison test, you have a little bit more freedom to pick what your comparison series is going to be. Because the thing with the limit comparison test is there isn't really such thing as a wrong comparison. There's plenty of examples of a bad comparison that won't really tell you anything, but there isn't really anything that's necessarily wrong. And so usually the safe thing to do is to come up with a comparison series that is pretty simple, that is still similar to your original series, that you know will, I guess, get you closer to an answer. And so in this case, I would use, for my comparison series, so if I said that, I'm going to say that series A is going to be equal to our original series, so sine of 1 over n. And for our comparison series, I'm going to say that it's going to be equal to just 1 over n. And this will be enough to get us to a conclusion. And you'll see why. And before I do anything, if you remember what the conditions are for a limit comparison test, it says that if you take the limit as, I guess, as in this case n, as n approaches infinity of an over bn, if that limit is if that limit is greater than 0, and less than infinity, so some real number that's greater than 0 and less than infinity, then your original series is going to behave the way your comparison series behaves. And then I'll say that that A behaves like B. And so if B diverges, then A would also diverge in this case. And then if B converges, then A would also converge. And so that would probably be the most straightforward case for a limit comparison test. And then the other thing you have to look for is if the limit is equal to 0. So if the limit is equal to 0, then and then also you have to look for if if the limit goes to 0 and the comparison series B converges, then A, or your original series, will also converge. And then the other case is if the limit is equal to infinity. In that case, if the limit is infinity and your comparison series B diverges, then A, your original series, will also diverge. And then those are the conditions of a limit comparison test. Otherwise, it's going to be inconclusive. So let's set up our limit. Well, before we do that, let's also find the behavior of our comparison series here. And this 1 over n, that is the harmonic series. And so the harmonic series has a p-value of 1, since it's just n to the first power. And so when your p-value, so by the p-series test, the harmonic series is going to diverge, because when your p-value is less than or equal to 1, then it's going to diverge. And it only converges if your p-value is greater than 1. So we know that our comparison series is going to diverge. So I'll just write that here. Give me a second. And so for that, we can say that B diverges. And so now we can plug this into our limit. So we'd have a limit that says that the limit as n approaches infinity of sine of 1 over n divided by 1 over n. And to find this limit, we can use L'Hopital's rule, because if we just plug in infinity from here, we're going to get an indeterminate answer. So when we do our first pass of L'Hopital's rule, we end up with cosine of 1 over n times negative 1 over n squared over negative 1 over n squared. And then these are going to cancel. And so we end up finding the limit of just cosine of 1 over n. And so from here, we can just plug in infinity. And when we do that, we end up with, since this is a bottom-heavy fraction, it's just going to end up being cosine of 0. And so this limit is going to be equal to 1. And so as a result, we found that through the limit comparison test, starting from here, we found that the limit of the original series divided by our comparison series is equal to 1. And since 1 is a real number that's greater than 0 and less than infinity, we know that our original series is going to behave the way our comparison series behaves. And our comparison series diverges. And so that means that our original series here of sine of 1n is also going to diverge. So the answer to this question is going to be C, because it's divergent by the limit comparison test with the series 1 over n. So yeah. All right, so we are given two series with the positive terms of s sub 1 is equal to a sub k and s sub 2 is equal to b sub k. And we further know that the limit as k approaches infinity of a sub k plus 1 over a sub k is equal to 1/2, and the limit as k approaches infinity of b sub k over a sub k is equal to 2. So what can we say about the convergence of these two series based on the given information? So there's a couple important things to note here. So it says that our two series have the two series that we have, they have positive terms. So they've clarified that it's only positive terms, which eliminates the possibility of an alternating series. So we don't have to worry about the additional conditions that you have to worry about when dealing with an alternating series. And so that makes our job a little bit easier. And so the other thing we have to look at is we have to look at the behavior of these limits here. And what you'll notice is that these limits they take the form of the general limits that you'd find when you're doing a ratio test. Like this limit looks like something you do when you're doing a ratio test. And this limit looks like something that you do when you're doing a limit comparison test. And the reason I know this is because recall that the ratio test says that to find the convergence of a series using the ratio test, you'd have to take the limit as k approaches infinity of a sub k plus 1 over a sub k. And if that limit is less than 1, if that limit ends up being less than 1, then the series is going to converge. And if the limit is greater than 1, then the limit is going to if the limit is greater than 1, then the series is going to diverge. And then if it's equal to 1, then it's going to be inconclusive. And then what you can see here is that in this first limit right here, you can see that the limit ends up being equal to 1/2 while taking the form of the ratio test limit that I mentioned. So it's safe to assume that this is basically a ratio test limit, which would indicate that since this was done on the a sub k series over here, and the limit is equal to 1/2, which is less than 1, it's safe to assume that this series right here, this series converges. And so the next thing we can do is we can focus on the second series over here. And here, this is what I was talking about with the limit comparison. Basically, what this limit did, or what they did for this limit, is they used this series, so a sub k, as a comparison series with the b sub k series to try to come to a conclusion using the limit comparison test. So if you recall, the limit comparison test says that if the limit as k approaches infinity of your original series, in this case the original series is b, so I'm going to say b, and the comparison series is a, so I'm going to say a. If this limit is some real number that's greater than 0 and less than infinity, then that says that that your original series is going to behave the way your comparison series behaves. And since this limit comparison is using this series as the comparison series, and we already concluded that that series converges with the ratio test over here, we can say that this series also converges because the limit that we found here was equal to 2, which is a real number between 0 and infinity. And so what we can deduce from here is that both of these series, so a sub k and b sub k, are going to be convergent. And so as a result, the answer to this question is going to be D. All right, which of the following statements is correct about the convergence of the series S sub 1 equals this thing over here, and S sub 2 is equal to this thing over here? And so both of the series that we're dealing with here are going to be an alternating series, and I know that because both of these have a -1 to the k term, and so that's what makes it an alternating series. So we're going to have to deal with a couple of other additional conditions when looking at the behavior of these series, rather than just convergence and divergence, because with an alternating series, you have a absolute convergence, conditional convergence, as well as divergence. And so the conditions for an alternating series, I'll write them down over here. What you do basically is you look at the absolute value of the series first, and what that does is that effectively makes it, you're effectively treating it like a normal series that's not alternating when you do that. And so basically, if the absolute value of a series, let's just say a sub k, if this converges, then the original series, including the alternating part, just a sub k, is going to converge absolutely. And then in the flip side, if you have a case where the absolute value diverges, that's when things start to get a little complicated, because from there we have to check for conditional convergence. And so in those situations, there's two things you have to look for when checking for conditional convergence. That being that you need to take the limit to infinity of the original series and see if that goes to 0. And if it goes to 0, that's one of the conditions satisfied. And the next thing you have to do is you need to confirm that a sub k is a decreasing series. And if both of these conditions are met, then a sub k is going to converge conditionally. Otherwise, if none of these things are met, it's going to diverge. And so so to summarize, if the absolute value of the series converges, then the series is going to converge absolutely. And if the absolute value diverges, then you have to do this stuff over here and check for these conditions. And then if it meets those conditions, then the series will converge conditionally. And so so now now I'm going to move on to the first series S sub 1. And so first, let's take the absolute value of that to get rid of the alternating portion, and that'll give us root k over k plus 4. And so now to check the convergence of this, I'm leaning towards using some sort of comparison test for that, and I'm going to use the limit comparison test. And the reason why is because even though the direct comparison test might be a little more straightforward, with the limit comparison test, you don't have to worry about making sure that your comparison series is greater than or less than your original series and doing stuff accordingly with that. You have a little bit more freedom with what you want to use for your comparison series when you're doing a limit comparison. Even if the limit computation is more intensive, you have a little bit more freedom. And I think that's nice because generally speaking, when you make a comparison series, you want to come up with something that's similar to the original series while being as simple as possible, because that'll give you the best idea of what's going on with the series. So in this case, for example, if s sub 1 is this, so s sub 1 equals this, or the absolute value of that is. So for my comparison series, I'll just say that bk is going to be equal to root k over k, eliminating this 4 term, because this takes a form that's similar to our original series while being more simple to work with, because this will reduce to 1 over root k, and so which gives us a p series. And so we can just use the p series test to prove that our comparison series actually diverges, because this is equal to 1 over k to the 1/2, which gives us a p-value which is equal to 1/2. And with a p series, if your p-value is less than or equal to 1, then that means that your series diverges. So we know that our comparison series is going to diverge. So the next thing we have to do is we have to take the limit to infinity of the original series, so this s sub 1, over our comparison series of bk, and see what that limit goes to. And if that limit is greater, if it's greater than 0 and less than infinity, so we get some positive real number, then that's the most straightforward case. And in that case, that would mean that the original series is going to behave the way the comparison series behaves. And so in this case, since our comparison series is diverging, if our limit evaluates to some real number between 0 and infinity, then our original series is also going to diverge. So that limit is going to end up looking something like the limit as k approaches infinity of root k over k plus 4 divided by 1 over root k. And then this can be further simplified to just when we divide things out, you end up with k over k plus 4. And from here, finding the limits, we can just do L'Hopital's rule, and when we differentiate that, you end up with just 1 over 1, which equals 1. So our limit evaluates to 1, which is between 0 and infinity. So we know that the absolute value of s sub 1 is going to diverge. And so now we have to check for conditional convergence. And so to do that, the first thing I'm going to check is to see if our series is decreasing. And one of the ways you can do that mathematically is by taking the derivative of the series and seeing if that derivative is negative. So I'm going to do that. And then also for the differentiation, you don't have to take into account the alternating portion here. So even though we're not dealing with absolute values anymore, so we know that s sub 1 is equal to, no, that is not a sigma. S sub 1 is equal to the square root of k over k plus 4. So s sub 1 prime would be equal to we can find the derivative of this using quotient rule. So you'd end up with 1 over 2 root k times k plus 4 minus 1 times root k over k plus 4 squared. And this looks a little messy, so I'm gonna simplify things a little bit. And when we do that, this can be reduced to be equal to negative root k plus k plus 4 over 2 root k over k plus 4 squared. And the reason why I moved this to the front is because this term is always going to be greater than this term, and since it's a negative, this is how we can prove that the derivative is in fact negative. This will always be less than 0. And so as a result, yeah, we were able to prove that the series is decreasing. And the next thing we have to do is we need to evaluate the limit of it, the original series, without anything else and see if it goes to 0. And so when we do that, I'll set up the limit here. So we have the limit as k approaches infinity of the square root of k over k plus 4. Now, finding this limit is going to be a little more annoying because we can't just use L'Hopital's rule to turn everything into a bunch of constants, because we have a radical here. So no matter how many times we differentiate this, we'll never get a constant. And so instead, what I'm going to do is I'm going to move things around in a way that can get us somewhere. And so the first thing I'm going to do is I'm going to rewrite this as the square root of k over k times 1 over 1 plus 4 over k. And so I removed the k's from the original fraction here. And it's okay that there's a k in the denominator here. I want that actually, because from here I can reduce this, and this will just become equal to 1 over root k times 1 over 1 plus 4 over k, which would be equal to that would be equal to 1 over root k over 1 plus 4 over k. And so from here, this is what I want, because we have a bunch of bottom-heavy fractions here. And bottom-heavy fractions are good when you're dealing with infinity, because when you plug in infinity here, these fractions are just going to go to 0. So this just ends up being equal to 1 over 0 over 1 plus... Oh, wait, not 0, 0. 1 over infinity over 1 plus 4 over infinity, which just equals 0 over 1 plus 0, which just equals 0. And so we've satisfied the two conditions for conditional convergence. We found that the series is decreasing by taking the derivative of it and finding that it's negative, and then taking the limit of that original series and finding that it went to 0. So as a result, S sub 1 is going to converge conditionally. And so now we can move on to the next series of S sub 2. And for S sub 2, I'm going to take a similar approach. And so the first thing we're going to do is we need to check for absolute convergence. And so similar to the first term, I am going to use a, I'm going to actually, no. We don't, this is the second series is actually going to be easier to work with. We can say that the absolute value of S sub 2 is going to be equal to 2k squared over 3k squared plus 1. And we don't have to, we can just test for divergence by doing a divergence test on this, because when we take the limit of this, the limit as k approaches infinity, we end up with 2k squared over 2k squared, no, 3k squared plus 1. And when you apply L'Hopital's rule, this is just going to, a bunch of times, this is going to just turn into 2/3. And the divergence test tells us that if the limit of the series as it approaches infinity is not equal to 0, then it diverges. So we know right off the bat that the absolute value of S sub 2 is going to diverge. And so, but since we're dealing with an alternating series, now we have to check for conditional convergence in a similar fashion to the first series. And so to do that, the thing is, we don't even have to check that that this converges conditionally, because we already know that the limit goes to 2/3. And in order for conditional convergence, the limit has to go to 0 and the series has to be decreasing. And since we know that the limit goes to 2/3, we know that's already one of the conditions not being met, and so we know that not even conditional convergence is possible with S sub 2. So as a result, S sub 2 is going to diverge. And so now we can pick an answer. And for that, the answer would, I believe it's going to be C. Yeah. So yes, the answer to this question is going to be C.